Okay, so let's look at another example. This one is probably a little bit simpler. So we have 3 books, right? I've labeled them as A, B, C, right, on top of each other, stacked on top of each other. We want to draw a free body diagram of each of those books. So let's start with the top one, A, okay? So A is interacting with the book B, right? And it's interacting with the gravitational pull. So you have the normal reaction from the B applied on A in the upward direction. That's NA-B, and the weight is MAG, right? Simple. Let's look at the book B. Book B is interacting with book A and book C. What is the job of book A? Book A is pushing down on B, and what is that normal reaction? It's this NA-B pointing downward, right? Okay, oops. And then we have the weight of the book, and then we have the normal reaction from the C on the B on the bottom surface of the B, because C is going to be pushing B up, because C is supporting B, so we have NB-C, right? Okay. What about C? C is on the floor, and I didn't draw the floor. I should have actually drawn the floor. C is supported by the floor, and or the table maybe. So you have the NC-ground pushing it up. You have the gravity, and you have the normal reaction from the B on the C. That's NB-C. Right? So essentially, we have how many unknowns here? We have NA-B, NB-C, and NC-ground. Right? That's a free body diagram. Any questions about this? Why am I using the normal reaction? Instead of the weight of what? The book above it. Okay, I was hoping somebody would ask that question, so thanks for asking that. So I'm pretty sure some of you have this question, but are afraid to ask it, or shy enough to ask this question. So what he's asking is that you have B over here, and A is on top of B, right? So B will experience some weight of A, right? Similarly, C will experience the weight of both A and B on top of it. So how are we accounting for those? How are we accounting for those? Well, we are accounting for those, but here's the thing. Gravitational pull is an interaction between an object and the gravitational attraction of the Earth, right? The way you are accounting for the weight of A and B is indirectly through these normal reactions. So if there was no weight of this, there would be no normal reaction, right? So if you look at A and assume that A is not going anywhere, which means it has no acceleration, so from Newton's second law, some of the forces on A should be equal to 0, then NA-B would be equal to the weight of A, right? And if you look at B, and if B is not going anywhere, then all the forces would be balanced on B as well. In that case, the NB-C would be equal to the weight of B plus NA-B, which is nothing but the weight of A. So you do get that, right? It's just that you are accounting for the weight of the things above an object of interest indirectly through the normal reaction. What if it's an incline? Doesn't matter. It's the same thing. It doesn't matter whether it's an incline or not. You only have to worry about the interaction. So if you're drawing free body diagram, you need to ask this question from yourself. What are the other objects in its surrounding that this is interacting with? And that's it. Sorry, I couldn't hear you. The normal force on the top and the bottom? Well, they may or may not be same. You can compute what they would be, right? This is not an exercise I want to do right now because I want to get to the equilibrium analysis first, but we could do it now that you guys are asking. So NA-B would be equal to MAG, and this is for book A, right? The normal reaction on the book A is same as this weight. If you look here, both of these forces are pointing downward. This one is pointing upward. If this is an equilibrium, if it is not going anywhere, then all the forces should balance, which means that this should be equal to NA-B plus MBG. And we just saw that this is equal to MAG, so this is nothing but MA plus MB times G. Right? Let's come to this one. NC ground would be equal to NB-C plus MBG. Right? And we just saw NB-C is equal to this quantity, so this would be MA plus MB plus, well, sorry, this is MC times G. So which means that the normal reaction from the ground on C would have to be equal to the weight of all the three books. And that makes a lot of sense. right? Because if you were to draw a free body diagram of A, B, and C together as a system, what forces would you show? You would only show the normal reaction from the ground, and you'll show all the gravitational pull, and they'll balance out. So you'll get the same answer. Yes? Does that answer your question? Right? Okay, so this is a practice, right? So we want to create a free body diagram for the sled and for the sled with the children pictured below, right? So first is, how do we draw free body diagram for the sled alone, minus the kids, right? That's what we want to do. So we have the sled over here. Let me first write free body diagram of the sled. And this is the rope. So somebody's pulling on the rope, assuming, right? So what are the forces acting on the sled? We have the tension. Somebody's pulling on the rope. We have the weight of the sled. Let's call it W, right? We have the normal reaction from the kids. Let's assume they're a particle. So we have the normal reaction from the kids. We have the normal reaction from the ground. Let's call it N ground. And we will call this N sub kids. Okay? Any other forces on the sled? Friction force. So if the sled is sliding, then you also have the force of friction from the ground. Anything else? So if the kids sitting in the sled are not sliding with respect to the sled, then there has to be a friction force exerted by the kids on the sled as well, right? If there is a relative motion, if there is no friction between them, then it's not a problem. But assuming, and that's what happens in most of the cases, if the kids are not sliding inside the sled, right, they stay where they are, then there will also be a force of friction, let's call it F sub F1, between the kids and the sled, right? If you wanted to draw the free body diagram for the sled with the children, that'll be an even easier one, because both of these forces would be internal forces. So the only forces would be all of these that you're showing, plus the weight of the kids, right? Okay.